PNUS. Good evening, space enthusiasts. On July 1, 2025, the astronomical community was stunned by an extraordinary discovery. A telescope in Chile detected a celestial body whose existence seemed to defy all known laws of the universe. This enigmatic object was moving at an astounding speed of 68 kilometers per second, along a trajectory deemed the most extreme ever recorded. Its orbital eccentricity, by all calculations, completely violated the fundamental principles of physics known to humanity. This visitor from the depths of space was officially designated 3I Atlas, becoming the third confirmed interstellar object to penetrate our solar system. However, unlike its mysterious predecessor Oumuamua or the familiar comet Borisov, this cosmic wanderer displayed entirely different characteristics. It surpassed them in size, speed, and activity, making it the most remarkable object astronomers had ever encountered. This comet could be up to 24 kilometers across, potentially making it the largest interstellar visitor ever detected. It hurtled through space on a hyperbolic trajectory that would take it past Mars, then around the Sun, and eventually return it permanently to the boundless void of interstellar space. Humanity had only a few months to try and unravel its profound mysteries before it dissolved completely into the endless darkness between the stars. The world braced for one of the most shocking interstellar discoveries of our time. This astonishing story began late in the evening of July 1, 2025. Larry Dino, a talented software engineer whose work was closely tied to the Atlas telescope in Chile, was processing routine observation data. Suddenly, an unusual phenomenon caught his attention. A faint point of light of the 18th magnitude, rapidly moving through star fields near Jupiter's orbit at an utterly inconceivable speed. It seemed like a perfectly normal discovery, Dino later recalled. However, the preliminary calculations he performed instantly sent a chill down his spine. The object wasn't just moving fast, it exhibited speeds that by all laws should have been absolutely impossible for any body gravitationally bound to our solar system. At 68 kilometers per second relative to the Sun, this object was moving significantly faster than any object that is part of our solar system could. The Atlas Survey Telescope had accidentally stumbled upon something truly extraordinary. The celestial body, initially designated as the enigmatic A11P3Z, was entering the inner solar system from the direction of the constellation Sagittarius, seemingly arriving from the very heart of our galaxy. Yet this was no ordinary comet returning after millennia of wandering in the outer, boundless darkness. The mathematical calculations were absolutely irrefutable. Such incredible velocities guaranteed that objects would inevitably escape the Sun's gravitational grasp. Anything moving so swiftly simply cannot linger in our system for long. Instead of following a familiar elliptical orbit, the object's astonishing speed traced a hyperbolic trajectory, a path that would carry it through the inner solar system and then sweep it back into the limitless interstellar void. Within hours, observatories worldwide swiftly turned their most powerful instruments toward this mysterious visitor. The Minor Planet Center received over 122 observations from 31 different observatories within the first 24 hours of the discovery. Professional astronomers and amateur observers alike realized they were witnessing something absolutely unprecedented in astronomical history. The object was officially designated 3I Atlas on July 2nd, making it only the third confirmed interstellar object ever detected passing through our solar system. The Roman numeral 3 placed it in a highly exclusive club that included the mysterious Oumuamua and the already familiar comet Borisov. However, 3I Atlas was already proving to be unlike anything astronomers had seen before. Early observations revealed something even more remarkable. This was not just a dead rock tumbling haphazardly through space. Telescopes detected clear signs of cometary activity, including a faint coma and a tail extending at least 25,000 kilometers into space. After millions of years drifting in the icy depths between stars, this ancient visitor was awakening to new life as our sun's energy began to gradually warm its icy surface. The discovery timeline was about to become even more shocking when amateur astronomers made a troubling discovery that NASA had seemingly overlooked. What NASA did not want the general public to know was that 3I Atlas had been visible in their telescopic images weeks before the official announcement of its discovery. Amateur astronomer Sam Dean, working from his home computer, systematically reviewed archival Atlas data and made a truly shocking find. Dean discovered clear images of the interstellar visitor dating from June 25th to June 29th, extending the observation timeline by critical weeks. But that wasn't all. Yaquensi discovered even earlier observations from the Zwicky Transient Facility, spanning June 14th to June 21st. The evidence was absolutely irrefutable. This cosmic visitor, subsequently designated 3I Atlas, had been captured in photographs repeatedly before specialists in the professional astronomical community could truly recognize what they were observing. Sam Dean suggested that 3I Atlas was not detected earlier because its path lay through the dense star fields of the galactic center. Under such conditions, the comet would have been extremely difficult to distinguish among billions of background stars. Thus, the object was effectively hiding in plain sight, cleverly disguised against the most crowded and star-rich region of the night sky. The extended observation timeline provided the opportunity to calculate the object's true trajectory with astonishing precision. With weeks of data rather than just days, astronomers were able to determine that 3I Atlas has an orbital eccentricity of 6.2. This value represents the most extreme trajectory ever recorded for any celestial body passing through our solar system. To fully grasp how unusual this number is, consider that Earth's orbit has an eccentricity close to zero, corresponding to a nearly perfect circle. Even Halley's Comet, despite its highly elongated 76-year orbit, reaches an eccentricity no greater than 1. When eccentricity exceeds 1, objects follow hyperbolic trajectories that bring them into our solar system only once, never to return. However, an eccentricity of 6.2 represents something almost beyond human comprehension. Amateur astronomers, through their observations, revealed a fundamental flaw in the functioning of our detection systems. The legitimate question arises: how many more interstellar visitors might have passed unnoticed simply because their journey took them through inconvenient areas of the sky? Professor John Tonry, representing the University of Hawaii, acknowledged that a significant number of interstellar objects cross the inner part of our solar system annually, although 3I Atlas is by far the largest of them. Preliminary observations also shed light on why automated systems had not flagged this object earlier. The comet was moving through the galactic plane, where the density of stars reaches its maximum concentration, creating visual chaos that confused detection algorithms. These algorithms were designed to identify moving objects against a relatively empty background, which proved ineffective in this case. This discovery triggered alarming questions regarding our planetary defense capabilities. If we failed to detect a massive interstellar comet for several weeks, what else might be approaching us unnoticed? The answer to this question would soon become evident as astronomers realized the true scale of this cosmic invasion. 3I Atlas is moving at a speed of 68 kilometers per second relative to our Sun. This rate breaks all previous speed records for interstellar visitors and redefines our understanding of what is considered possible for objects traveling between star systems. To fully grasp this incredible speed, imagine being able to travel from New York to Los Angeles in less than 90 seconds, or circumnavigate the entire planet Earth in under 10 minutes. This speed is so extreme that it places 3I Atlas in a category beyond anything observed thus far. The mysterious Oumuamua reached a speed of 26 kilometers per second, while Comet Borisov moved at 32 kilometers per second. 3I Atlas is traveling more than twice as fast as any confirmed interstellar object in documented history. Such speeds ensure that objects can escape the Sun's gravitational grasp without slowing down. The escape velocity from our solar system varies depending on the distance from the Sun, but typically ranges from 42 to 45 kilometers per second. 3I Atlas exceeds this threshold by such a significant margin that our sun's gravity has virtually no impact on its trajectory. The physics of such extraordinary speed tells a story of cosmic violence that occurred millions of years ago in a distant star system. Objects do not achieve such speeds through gentle gravitational nudges. 3I Atlas likely originated from the vicinity of another planetary system, where it was ejected from its orbit around a foreign sun due to catastrophic gravitational interactions with a giant planet or a passing star. Analysis of the comet's trajectory shows that it approached from the general direction of Sagittarius, where the central region of our galaxy is located. This path suggests that it may have originated in the galactic disk, the flat plane where most of the Milky Way's stars are concentrated. Computer models suggest that achieving such extreme speeds requires either multiple gravitational encounters or single catastrophic events. Binary star systems, supernova explosions, or close encounters with stellar black holes could have provided the immense energy needed to accelerate objects to such velocities. The comet likely traveled through interstellar space for millions or even billions of years before recently arriving in our solar system. What makes this incredible speed even more astonishing is the lack of any signs of deceleration for 3I Atlas. Unlike celestial bodies that form within our solar system and follow predictable elliptical trajectories, this cosmic visitor will maintain its striking velocity as it sweeps past the sun and continues its endless journey into the cosmic abyss. The comet's hyperbolic excess velocity far from the sun is approximately 60 kilometers per second, irrefutably confirming that it will exit our solar system almost as swiftly as it entered, after its fleeting visit to our cosmic neighborhood. 3I Atlas will dissipate into the interstellar void, carrying all its secrets back into the galactic darkness. However, this record-breaking speed poses a serious challenge for astronomers who are rushing to study this cosmic messenger before it disappears from sight forever. The orbital eccentricity of 6.2 that characterizes 3I Atlas represents a mathematical value so extreme that it defies our current understanding of what is even possible in the realm of gravitational dynamics. This number carries the story of the most violent cosmic event ever recorded in the vicinity of our solar system. To fully comprehend orbital eccentricity, one must understand the fundamental shapes along which objects can move in space. A perfect circle has an eccentricity of 0, representing the most stable orbit possible. Earth's slightly elongated path around the Sun is just 0.017, keeping our planet at a nearly constant distance from our star throughout the year. Most objects in our solar system follow similar, well-understood orbits. Even highly elongated trajectories, such as that of Halley's Comet, achieve an eccentricity of only 0.967. These are called bound orbits, representing mathematical curves that close upon themselves and repeat infinitely. When eccentricity exceeds 1, the fundamental mathematical logic changes entirely. Objects begin to follow hyperbolic trajectories, open curves that extend to infinity, never returning. This is the defining characteristic of interstellar objects. Their hyperbolic orbital paths irrefutably prove that they originated outside our solar system and will never return. However, an eccentricity of 6.2 represents something almost beyond theoretical limits. 3I Atlas follows one of the most open hyperbolic trajectories, barely affected by our sun's gravitational field. Even during its closest approach, the object moves so quickly that solar gravity can only slightly deflect its path, like trying to change the direction of a bullet with a gentle breeze. Harvard astronomer Avi Loeb calculated that such extreme orbital parameters create unacceptably high mass densities in interstellar space, unless 3I Atlas represents an incredibly rare population of cosmic wanderers. Mathematical calculations suggest that either this object is significantly smaller than initial estimates indicate, or interstellar visitors like it are much rarer than previously assumed. Nevertheless, 3I Atlas appears to exhibit weak activity compared to the other known interstellar comet, Borisov. This observation may indicate that 3I Atlas indeed possesses a significantly larger nucleus, which, however, produces less gas and dust per unit area of its surface. Such behavior could suggest a different composition or internal structure compared to typical comets residing in the solar system. The uncertainty in determining the comet's size is partly due to its extremely faint apparent magnitude, which ranges from 17 to 18. This circumstance requires the use of sophisticated telescopes and exceptional viewing conditions for its detection. Most amateur telescopes are unable to detect objects fainter than the 15th magnitude, making this interstellar visitor inaccessible to casual observations. Nevertheless, advanced observatories, including the infrared capabilities of the James Webb Space Telescope, should soon help clarify the true size and composition of 3I Atlas. Infrared observations are capable of detecting thermal radiation directly from the solid nucleus, allowing differentiation between heat emanating from the nucleus and reflected sunlight scattered by the surrounding dust cloud. A larger nucleus size has profound implications for understanding the violent processes that eject objects from their native planetary systems into the vast expanses of interstellar space. Humanity's time to study 3I Atlas is rapidly running out, creating an unprecedented urgency within the global astronomical community, as this once-in-a-generation opportunity threatens to slip away forever. The comet will remain observable until September 2025, after which it will pass too close to the Sun for safe telescopic observations. Solar glare will then obscure the object until early December, when it will reappear on the opposite side of our star, already beginning its exit from the solar system. Planetary astronomer Kretke, as soon as he heard about the comet, immediately began observing it with the Discovery Channel telescope at Lowell Observatory in Arizona. He expressed confidence that it would only be a couple of weeks before almost every major telescope on Earth and in space would allocate time to detect and track this unique comet. People are excited. Almost every planetary astronomer I know immediately ran to a telescope or sent emails requesting telescope time in the next few days, Kretke reported. While we may have a few months to study this fascinating object, the sooner we can understand how it works, the faster we can plan the rest of its passage through the solar system. Astronomers at the European Space Agency are actively tracking this object with telescopes located worldwide as part of their broader mission to detect and characterize potentially hazardous objects. By the time 3I Atlas was officially announced, the Minor Planet Center had already collected 122 observations from 31 different observatories. The task of observing this unique cosmic object is significantly complicated because the interstellar comet 3I Atlas currently has an apparent magnitude ranging from 17 to 18. This means that its detection requires not only sophisticated astronomical instruments, but also exceptionally dark skies. According to current calculations, the comet's brightness may increase to the 16th magnitude by the end of July. However, it should be emphasized that all these predictions remain highly uncertain given our extremely limited experience with such interstellar visitors. The situation becomes even more difficult as the comet approaches perihelion, its closest point to the Sun. Between October 2nd and November 10th, 3I Atlas will be less than 30 degrees from our star, making observations with ground-based telescopes extremely challenging or even entirely impossible. Currently, the comet is located approximately 4.5 times farther from the Sun than Earth. Nevertheless, it will reach its closest point to the Sun on October 30th, approaching our home star to a distance of 1.4 astronomical units. Shortly before this moment, the comet will also make its closest approach to Mars, coming within 0.4 astronomical units of the red planet. During this close encounter with Mars, the comet, from the planet's perspective, could reach an apparent magnitude of 11. This means that orbiters in Mars's orbit will have the opportunity to observe it in unprecedented detail. Such an event represents a unique opportunity for spacecraft already operating in the Martian system to study an interstellar visitor up close. After 3I Atlas disappears behind the Sun, it will reappear in early December, providing astronomers with another temporary window for its study. Although the comet will be significantly fainter and less active on its outward journey, the December reappearance is humanity's last chance to investigate this cosmic messenger before it disappears forever into the vast expanses of interstellar space. The distinctly reddish glow surrounding Comet 3I Atlas tells an ancient story recorded in cosmic dust, revealing precious secrets about its mysterious origin and chemical composition from an alien star system. Observations made using the LBT, Large Binocular Telescope, clearly demonstrate that the comet's evolving coma has a reddish hue, unequivocally indicating the presence of complex organic compounds and dust particles. This characteristic coloration is strikingly similar to that previously observed around Borisov, the previous interstellar comet. This resemblance strongly suggests fundamentally similar formation processes in the cold outer regions of different planetary systems. Northern Optical Telescope observations, performed by renowned astronomers David Jewett and Jane Liu, confirmed that 3I Atlas exhibited clear activity, possessing a diffuse tail. Miguel Larón and his team from the Institute of Astrophysics of the Canary Islands also recorded cometary activity, with a tail extending at least 25,000 kilometers into space. The reddish coloration provides important scientific information about the chemical processes that occurred during the comet's formation billions of years ago. Complex organic molecules form through various pathways during the evolution of planetary systems, and their presence reveals data about the potential for prebiotic chemistry in extraterrestrial environments. Spectroscopic analysis of the outgoing gases and dust will reveal the detailed chemical composition of 3I Atlas's ancient nucleus, providing direct samples of material from another planetary system. Each molecule has a unique spectral fingerprint, allowing astronomers to identify water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and increasingly complex organic compounds in the expanding coma. The released dust particles contain invaluable information about the high-temperature processes that took place during the early formation of the comet's parent system. These microscopic grains preserve records of condensation sequences, thermal processing, and dynamic mixing that shape the distribution of materials throughout the initial protoplanetary disk. The size distribution of dust particles provides additional insights into the nature of the comet's activity. Larger particles indicate recent surface activity of the nucleus, while smaller grains may have been processed by cosmic radiation during the long interstellar journey. The observed ratio between different particle sizes helps determine how active the comet was in its original system compared to how much material is being released now. Closer investigations with more powerful observatories, including the infrared capabilities of the James Webb Space Telescope, should soon help clarify the composition of 3I Atlas in unprecedented detail. Infrared observations can detect thermal radiation from microscopic dust grains, revealing their precise temperature, size distribution, and chemical composition. The chemical signatures preserved in 3I Atlas represent some of the purest materials available for studying conditions in another star system, offering insights into planet formation processes throughout the galaxy. Throughout its millions and possibly billions of years of existence, interstellar comet 3I Atlas has endured the most extreme survival conditions known in the universe. It drifted silently in the icy interstellar void, where temperatures plummet to absolute zero and deadly cosmic radiation continuously bombards every exposed surface. During its incredibly long journey through interstellar space, the comet encountered temperatures reaching -270 degrees Celsius. This was enough to transform any known material into brittle crystalline structures. At such unimaginably low temperatures, most chemical reactions cease entirely, and the movement of individual atoms within molecules slows to almost imperceptible levels. The radiation environment of deep space presents equally harsh and challenging conditions for survival. High-energy cosmic rays, accelerated to colossal speeds by distant supernovae and other violent cosmic events, relentlessly bombarded the comet's surface throughout its multi-million-year journey. These powerful particles are capable of disrupting complex molecular structures and gradually altering the chemical composition of materials on the surface. Galactic cosmic radiation includes a wide range of particles, from individual protons and electrons to heavy atomic nuclei, moving at significant fractions of the speed of light. When these particles collide with the comet's surface, they generate cascades of secondary radiation that can penetrate several meters into solid ice and rock, potentially altering subsurface materials that will only be exposed when the comet reactivates. Despite these incredibly harsh conditions, Comet 3I Atlas appears to have remarkably preserved its structural integrity and chemical composition. This is evidenced by its ability to form a normal coma and tail when heated by our Sun. The fact that it is able to outgas normally suggests that internal ice deposits remain largely uncontaminated by radiation damage or thermal cycling effects. The survival of this comet provides invaluable insights into the resilience of materials in extreme environments. Understanding how complex molecules and icy structures can withstand millions of years of radiation exposure has important implications for astrobiology and the potential preservation of organic compounds in cosmic environments. Theoretical models suggest that objects like 3I Atlas can maintain a viable chemical composition for tens of millions of years during interstellar travel, potentially transporting complex organic molecules between star systems. This possibility raises fascinating questions about whether the building blocks of life can sometimes be spread across the galaxy via interstellar objects. Surface layers exposed to direct radiation during the journey may have developed protective crusts that effectively helped preserve the underlying materials from further damage. This creates natural time capsules of pristine ancient material that formed in a completely different stellar environment. The successful preservation of volatile compounds during such a long cosmic odyssey demonstrates the remarkable stability of materials in extreme space conditions. The extreme speed of 3I Atlas tells a story of catastrophic violence that occurred millions of years ago, when this cosmic wanderer was violently ejected from its home system by forces that transformed an ordinary comet into a galactic bullet hurtling through space. Objects do not achieve such enormous speeds through gentle gravitational nudges. 3I Atlas most likely originated from the vicinity of some other planetary system, where it was ejected from its orbit around an alien sun as a result of catastrophic gravitational interactions with a giant planet or a passing star. The physics of such extraordinary acceleration involves scenarios that would utterly destroy smaller objects. Multiple successive encounters with giant planets can create devastating gravitational slingshot effects, with each gravitational interaction adding immense energy to the object's motion. Computer simulations show that objects can sometimes achieve hyperbolic escape velocities through precisely calculated planetary encounters during periods of orbital instability. Close stellar encounters represent another effective mechanism for achieving such extreme speeds. When two star systems sweep past each other within a few light-years, their powerful gravitational fields begin to interact actively, leading to the ejection of objects from the outer regions of planetary systems directly into interstellar space at incredibly high velocities. The gravitational chaos that arises during such close passes is capable of accelerating celestial bodies far beyond their usual escape velocities. Binary star systems offer additional opportunities for this type of energetic ejection. In cases where two stars are in a close gravitational dance, objects located in their outer regions are subjected to complex three-body gravitational effects. This sometimes leads to the formation of hyperbolic ejection trajectories. The gravitational interaction between multiple massive objects generates chaotic dynamics capable of unpredictably accelerating smaller bodies to truly extreme speeds. The most dramatic and grandiose ejection mechanisms are inextricably linked to the evolution of stars themselves. When massive stars reach the end of their life cycle and undergo colossal supernova explosions, an enormous release of energy occurs. This release is capable of accelerating nearby objects to significant fractions of the speed of light. Although the speed of 3I Atlas is significantly below such extreme levels, asymmetric supernova explosions or intense interactions with neutron stars could potentially provide the necessary acceleration for it. Recent theoretical studies suggest that planetary system instabilities during periods of so-called late heavy bombardment, similar to those experienced by our own solar system billions of years ago, regularly lead to the ejection of significant numbers of objects into interstellar space. These chaotic phases arise when giant planets migrate through evolving systems, gravitationally scattering countless smaller bodies. The violence that was required to achieve the current speed of 3I Atlas indicates that it survived one of the most extreme gravitational encounters while maintaining its integrity as a cohesive object. Understanding these diverse ejection mechanisms helps astronomers more accurately estimate how many interstellar objects should be moving through our galaxy at any given moment. The discovery of 3I Atlas provides shocking confirmation that our galaxy is literally filled with cosmic wanderers. John Tonry of the University of Hawaii reports that quite a few of them pass through our inner solar system each year. In this regard, 3I Atlas is by far the largest detected. This admission by a leading astronomer reveals an uncomfortable truth. Our current detection capabilities have been missing the vast majority of interstellar visitors. For every object that happens to be bright enough and fortunately positioned for detection by modern survey systems, dozens or even hundreds of similar cosmic wanderers likely pass completely unnoticed. Statistical analysis, based on 3 confirmed interstellar detections, strongly suggests that we are seeing only the tip of a massive iceberg. Detection bias heavily favors objects that happen to pass relatively close to Earth and arrive from convenient viewing angles. Interstellar visitors that cross the outer regions of our solar system, approach from problematic directions, or arrive during periods when ground-based telescopes cannot observe them, remain completely invisible to us. Current estimates suggest that at any given time, thousands of interstellar objects larger than a few meters could be present in our solar system. The vast majority remain undetectable due to their small size, significant distance, or unfavorable geometric circumstances for observation from Earth. Theoretical models predict that the size distribution of interstellar objects follows similar patterns to asteroids and comets in our solar system, with many more small objects than large ones. Although 3I Atlas represents an unusually large specimen, which contributed to its detection, the cosmic population likely consists primarily of much smaller bodies that modern technology cannot reliably identify. Mario Jurek, a distinguished astronomer at the University of Washington and head of the software department responsible for object detection at the Vera C. Rubin Observatory, explains that the newest equipment is designed to significantly increase the number of detectable visitors arriving from beyond our solar system. This will allow astronomers to conduct comprehensive studies of these objects as a holistic population, rather than viewing each discovery as a disparate and isolated event. The Rubin Observatory, once fully operational, is expected to detect 1 to 10 interstellar objects annually, representing a colossal increase compared to historical figures. Such a technological revolution effectively marks the end of an era when interstellar visitors were considered rare and entirely unexpected discoveries. The hidden population of interstellar objects most likely includes representatives from a multitude of diverse planetary systems located in our galactic neighborhood. Each such object is a unique carrier of information about its parent system, providing invaluable opportunities to study the chemical composition and formation processes of worlds that we cannot observe directly. Chris Lintott of Oxford University describes interstellar objects as our chance to accidentally study phenomena occurring in the rest of the galaxy, thereby providing profound insights into the evolution of planetary systems in diverse stellar environments. The accumulation of data from numerous interstellar objects will eventually enable comprehensive statistical comparisons between different stellar environments and their associated planetary building blocks, fundamentally changing our understanding of the prevalence of Earth-like worlds throughout the vast universe. October 29, 2025 will mark the moment when 3I Atlas makes its closest approach to our Sun, reaching perihelion at a distance of just 1.356 astronomical units. This event potentially could trigger the most spectacular cometary show ever observed from an interstellar visitor. As the comet approaches within 130 million kilometers of our star, placing it just inside Mars's orbit, solar heating will reach maximum intensity. This will cause massive outgassing events capable of transforming this cosmic wanderer into a bright and impressive spectacle, visible with powerful telescopes worldwide. The approach timeline reveals a series of dramatic encounters that will truly test the comet's structural integrity. On October 3, 3I Atlas will pass within 0.193 astronomical units of Mars, which is approximately 29 million kilometers from the red planet. This event will be the closest approach of any confirmed interstellar object to another planet in our solar system. Martian orbiters, including the Mars Reconnaissance Orbiter, Mars Express, and the HOPE probe, will have unprecedented opportunities to study the interstellar visitor up close. From Mars's perspective, the comet could reach an apparent magnitude of 11, making it easily detectable by spacecraft cameras and scientific instruments already in the Martian system. These observations are capable of providing the most detailed measurements ever obtained about the surface properties, composition, and activity of an interstellar object. Spacecraft will be able to track changes in the comet's coma and tail development as solar heating intensifies during the final approach to perihelion. Increasing solar energy will cause subsurface ices to sublimate at an accelerating rate, potentially exposing entirely fresh material that has remained unchanged since the comet's formation in another star system billions of years ago. Spectroscopic observations at this stage are capable of revealing the purest samples of alien chemistry ever analyzed. However, time presents a cruel irony for ground-based observers. When 3I Atlas reaches perihelion on October 29th, Earth will be on the opposite side of the Sun, making direct observation impossible at the moment of maximum activity. Ground-based telescopes will lose sight of the comet as it disappears behind solar glare. The comet will remain unobservable from Earth until early December, when it reappears on the far side of the Sun, already beginning its journey back into interstellar space. By then, 3I Atlas will be receding from the inner solar system, becoming fainter and less active as it moves away from the solar energy that caused its spectacular awakening. This observation window represents humanity's last opportunity to study this cosmic messenger, before it disappears into the void between stars, carrying its secrets back into the galactic darkness, where it will drift for millions of years before potentially encountering another star system. The James Webb Space Telescope represents the most powerful instrument available to humanity for unraveling the mysteries of Comet 3I Atlas, providing unprecedented opportunities capable of revealing the true composition and internal structure of this interstellar wanderer with astonishing clarity. The advanced infrared instruments on the Webb telescope have the unique ability to detect thermal radiation and molecular signatures that remain completely invisible to conventional optical telescopes, thereby opening entirely new horizons for understanding materials that have traveled to us from another star system. The telescope's strategic position at the L2 Lagrange point provides an ideal geometry for conducting sustained observations of the comet as it approaches the Sun and then passes its perihelion. The near-infrared spectrograph, NIR-SPEC, has the ability to simultaneously track hundreds of different wavelengths, allowing for the creation of detailed spectral maps. These maps clearly demonstrate the presence and quantitative content of a multitude of chemical elements in the expanding coma of Comet 3I Atlas. Water vapor, carbon monoxide, carbon dioxide, methane, ammonia, and complex organic compounds. All these substances emit characteristic infrared radiation that the Webb telescope can detect with astonishing precision. Webb's mid-infrared instrument, MIRI, in turn, offers additional capabilities for a comprehensive study of the thermal properties of the tiny dust particles ejected from the comet's nucleus. By measuring the infrared thermal radiation emitted by these microscopic grains, astronomers can determine their temperature, size distribution, and chemical composition with unparalleled accuracy. Thermal measurements provide crucial insights into the internal structure and activity of the comet. Different regions of its nucleus may heat up at varying rates as the comet approaches the Sun, leading to temperature fluctuations. These variations, in turn, reveal valuable information about the composition of the surface layers, the thermal properties of the subsurface regions, and the rotational characteristics of the celestial body. One of the most valuable capabilities of the Webb telescope is the detection of extremely faint infrared emission lines from trace substances that may be present in minute quantities in the comet's atmosphere. Such measurements potentially can identify complex organic molecules or unusual isotopic ratios that serve as clues to exotic chemical processes occurring in the terrestrial system. The telescope's exceptional stability and high sensitivity allow for time series observations that track the dynamics of changes in Comet 3I Atlas's activity as it approaches the Sun. These temporal measurements can demonstrate how different chemical substances react to increasing solar radiation, thereby providing profound insights into the physical structure and composition of the ancient nucleus. Webb's infrared capabilities also enable observations that penetrate through the dense dust coma to investigate the thermal radiation emanating directly from the solid nucleus. This direct view of the nucleus can yield precise estimates of its size and surface temperature measurements, which are impossible to obtain using optical wavelengths where dust scattering completely dominates the observed brightness. Coordinated observations conducted using multiple Webb telescope instruments will enable the creation of comprehensive portraits of Comet 3I Atlas. These portraits will combine chemical analysis, thermal mapping, and temporal monitoring into unified, interconnected scientific datasets. Such integrated measurements will provide the most detailed characterization ever obtained for an interstellar object. The results could radically change our understanding of planet formation processes around other stars and potentially reveal how common Earth-like worlds are throughout the cosmos. Comet 3I Atlas appears particularly bright because it passed opposition on June 25, 2025. This phenomenon led to a significant increase in the brightness of its surrounding dust cloud due to the so-called opposition surge effect, which misled initial estimates of the comet's size and created a kind of cosmic optical illusion. The opposition surge occurs when sunlight reflects directly off dust particles surrounding the comet's nucleus, resulting in enhanced brightness that can increase the apparent magnitude by 2 to 5 times. This phenomenon explains why Comet 3I Atlas appeared much larger than expected when astronomers first attempted to calculate its size based on brightness measurements. The timing of this opposition surge almost perfectly coincided with the comet's discovery, meaning that initial observations captured 3I Atlas at its peak brightness rather than in its usual appearance. Astronomers typically use the brightness of distant objects as an indicator of size, but the surge effect drastically skewed these calculations. Harvard astronomer Avi Loeb analyzed the brightness data and concluded that the combination of apparent size and calculated population density leads to unacceptably high mass densities in interstellar space. His calculations suggest that either 3I Atlas is much smaller than initial estimates indicate, or objects of this size represent an incredibly rare population. The opposition surge effect gradually diminishes as the comet moves away from the perfect alignment between Earth, the object, and the Sun. This means that current brightness measurements will show the comet's true baseline magnitude, allowing for more accurate size determinations as observational data accumulates. Current brightness estimates suggest that 3I Atlas may have a magnitude of 17 to 18 under normal conditions, significantly fainter than the enhanced brightness observed during opposition. This correction reduces size estimates from the initial maximum of 24 kilometers to more conservative ranges of 5 to 15 kilometers in diameter. The confusion highlights the challenges of studying interstellar objects with limited observational experience. Unlike solar system comets, which have been observed over multiple orbital cycles, interstellar visitors provide only short windows for observations with no opportunity for long-term brightness monitoring. The brightness surge also impacted spectroscopic observations, increasing the signal-to-noise ratio for chemical analysis. The enhanced brightness during opposition made it easier for telescopes to detect faint spectral lines from trace gases and complex molecules in the comet's coma. As 3I Atlas continues its approach to perihelion, astronomers will monitor how its brightness changes in response to increasing solar heating. These measurements will separate true brightness changes caused by activity from artificial enhancement due to opposition geometry. Lessons learned from this brightness surge will improve analysis methods for future interstellar visitors, ensuring that size estimates and activity measurements account for geometric effects that can significantly alter observed properties. Unlike the puzzling Oumuamua, which sparked wild speculation about alien technology, 3I Atlas behaves exactly as astronomers expect a normal interstellar comet to, following predictable physics without mysterious accelerations or unexplained properties that defied scientific explanation. When Oumuamua appeared in 2017, it immediately sparked intense scientific debate with its strange non-gravitational acceleration, highly unusual elongated shape, and complete lack of visible cometary activity. These perplexing characteristics led some prominent researchers to propose increasingly exotic explanations, including the truly controversial possibility of artificial origin. Harvard astronomer Avi Loeb famously argued that Oumuamua could represent alien technology, specifically a solar sail built by an extraterrestrial civilization. The object's acceleration pattern, unusual reflectivity, and elongated dimensions seemed inconsistent with natural cometary behavior, creating a scientific enigma that remains unresolved. 3I Atlas presents a completely different and refreshingly straightforward story. Early observations revealed unmistakable signs of normal cometary activity that perfectly matched theoretical predictions. Multiple telescopes detected a faint but distinctly visible coma and a tail extending at least 25,000 kilometers into space, definitively confirming its status as a genuine comet. The object exhibits all the expected properties of a comet that formed naturally in the cold outer regions of another planetary system. Its overall composition and behavior appear remarkably similar to comets found in our own Kuiper belt, strongly suggesting that universal physical processes govern comet formation in diverse stellar environments. In stark contrast to Oumuamua's deeply puzzling and unusual behavior, the interstellar object 3I Atlas exhibits entirely predictable orbital mechanics. It displays no anomalous accelerations or trajectory changes that might hint at exotic physics or artificial propulsion. This comet's path through our solar system precisely matches gravitational calculations based on its observed mass and velocity. Spectroscopic analysis reveals a normal cometary composition, including water vapor, carbon monoxide, and organic compounds, which is entirely consistent with expectations for objects formed in the outskirts of planetary systems. The reddish coloration of its coma indicates a dust content similar to the previous interstellar comet Borisov, confirming consistent formation processes for these celestial bodies. Object 3I Atlas represents exactly what scientists hope to discover. These are interstellar objects that teach us about planet formation through familiar, well-understood physics, rather than perplexing mysteries that challenge fundamental assumptions about how the cosmos functions. Mario Jurek describes 3I Atlas as a potential tiebreaker that could help determine whether Oumuamua was truly anomalous, or if the universe contains more exotic objects than previously thought. The normal behavior of 3I Atlas supports the hypothesis that most interstellar visitors will turn out to be ordinary comets and asteroids ejected from other planetary systems during the chaotic phases of their formation. October 3, 2025 will mark an unprecedented moment in space exploration. On this day, 3I Atlas will make its closest approach to Mars, just 29 million kilometers away, providing orbiting spacecraft with the best views ever obtained of an interstellar visitor. Martian orbiters, including the Mars Reconnaissance Orbiter, Mars Express, MAVEN, and the HOPE probe, will have extraordinary opportunities to study this cosmic wanderer with instruments originally designed for planetary science, but ideally suited for detailed cometary observations. From Mars's perspective, 3I Atlas could reach an apparent magnitude of 11 during its closest approach, making it easily detectable by high-resolution cameras and scientific instruments already in the Martian system. This level of brightness places the comet within the detection capabilities of existing spacecraft. The Mars Reconnaissance Orbiter's high-resolution imaging science experiment, HiRISE camera, capable of resolving objects smaller than 1 meter on the Martian surface, could potentially capture unprecedented detail of the comet's nucleus structure and surface features. These observations would provide the highest resolution images of an interstellar object ever obtained. Spectroscopic instruments aboard Martian orbiters are capable of analyzing the chemical composition of 3I Atlas's coma and tail with exceptional precision. MAVEN's ultraviolet spectrograph could detect trace gases and atmospheric outgassing processes, while Mars Express's infrared spectrometer could identify complex molecular species. The timing of the encounter allows for extended observation campaigns as the comet approaches, reaches its closest distance, and recedes from Mars. This temporal coverage enables scientists to track changes in cometary activity, coma development, and tail structure as solar heating intensifies during the final approach to perihelion. Observations from Mars will be complemented by simultaneous measurements from ground-based telescopes, creating a comprehensive three-dimensional view of the comet's structure and activity. Different viewing geometries provide stereoscopic information that cannot be obtained from a single vantage point. The European Space Agency's Mars Express mission plans coordinated observations with ground-based telescopes to maximize the scientific return from this rare opportunity. These measurements will create the most detailed characterization of an interstellar visitor's physical properties ever achieved. Such a close approach also opens up unique horizons for a comprehensive study of the gravitational interactions unfolding between the comet and Mars. Although 3I Atlas is too small to significantly influence the red planet's orbital motion, meticulous tracking of its trajectory can reveal subtle perturbations that in turn will allow for refinement of the comet's mass and internal structure. In the future, Martian missions could be specifically targeted at exploring interstellar objects, potentially including sample return expeditions capable of delivering fragments of alien worlds back to Earth for thorough laboratory analysis. The discovery of 3I Atlas perfectly coincides with a period of revolutionary transformation in astronomical survey capabilities, which promises to turn rare visits by interstellar guests into routine scientific observations, fundamentally changing our approach to studying these cosmic wanderers. The Vera C. Rubin Observatory, located in Chile, represents the most advanced sky survey system ever created by humanity. Designed to repeatedly scan the entire southern hemisphere sky every few nights for 10 years, its gigantic 3.2 gigapixel camera can capture images covering 3.5 degrees of the celestial sphere in just 15 seconds. Within its first week of operation, the Rubin Observatory has already discovered over 200 previously unknown asteroids, demonstrating its extraordinary ability to detect moving objects. This unprecedented detection rate far exceeds what all other ground-based and space observatories combined typically discover in an entire year. Mario Jurek explains that as the observatory's survey progresses, it is expected to discover significantly more visitors arriving from beyond our solar system, allowing astronomers to study them as an entire population rather than as disparate, isolated discoveries. Current estimates suggest that the observatory will detect 1 to 10 interstellar objects annually, once it reaches full operational capacity. Automated systems are capable of identifying potentially interesting objects within minutes of image acquisition, comparing new observations with previous data to flag anything that is moving, brightening, or exhibiting unusual behavior. This rapid data processing capability means that future interstellar guests will be detected and tracked from the very first moment they appear in view. The observatory's wide field of view and its rapid scanning capability will address the detection bias issues that almost caused 3I Atlas to go unnoticed. Even objects passing through dense star fields near the galactic center will be detected using sophisticated image processing algorithms specifically designed to identify subtle motion patterns. Future space survey systems will further revolutionize interstellar object detection by eliminating atmospheric limitations and providing continuous sky coverage. Planned European Space Agency missions could detect much fainter objects across wider areas of the sky, potentially revealing the true abundance of cosmic wanderers. Advanced artificial intelligence systems will process unprecedented volumes of data, identifying scientifically interesting targets among millions of routine observations. Machine learning algorithms, trained on data obtained from 3I Atlas, as well as future discoveries, will significantly enhance detection efficiency and reduce false positives. The statistical sample of interstellar objects will become extensive enough to answer fundamental questions about the evolution of planetary systems throughout the galaxy. Comprehensive catalogs will reveal size distributions, compositional variations, and origin patterns that shed light on how different types of stars produce and eject the building blocks of planets. Long-term surveys spanning decades will track how interstellar object populations change over time, potentially revealing periodic variations related to galactic dynamics or stellar evolution cycles. This technological revolution ensures that 3I Atlas represents only the beginning, not the culmination, of interstellar object science. After Comet 3I Atlas completes its spectacular passage through the vicinity of the Sun and begins its steady journey back into the boundless expanses of interstellar space, it will carry all its cherished secrets into the cosmic void, never to return to our solar system or any other star system for millions of years. The hyperbolic trajectory of this celestial wanderer ensures that it will leave our solar system with virtually the same dizzying speed with which it entered, approximately 68 kilometers per second relative to the Sun. Having gained additional speed due to solar gravitational acceleration during its perihelion passage, 3I Atlas will hurtle outward, passing the orbits of the mighty giant planets, Jupiter, Saturn, Uranus, and Neptune. By March 16, 2026, the comet will pass within 54 million kilometers of Jupiter, receiving a final significant gravitational boost that will further increase its escape velocity from our system. This fateful encounter represents the last substantial gravitational interaction that 3I Atlas will experience before permanently departing our cosmic neighborhood. Once far beyond Neptune's orbit, the comet will begin its return journey into the icy and silent depths of interstellar space, where temperatures approach absolute zero and deadly cosmic radiation will relentlessly alter its surface composition for millions of years. The active coma and majestic tail will gradually disappear as solar heating diminishes, leaving only a dark, inactive nucleus, silently drifting in the boundless void. The journey back to interstellar conditions will take decades, as 3I Atlas slowly recedes from the weakening solar influence. At distances greater than 1,000 astronomical units, the Sun will appear as just another shimmering star against the immense cosmic background, exerting negligible heating or gravitational effect. During its long and solitary journey through the galaxy, 3I Atlas will inevitably encounter the gravitational fields of other stars, potentially altering its trajectory and speed over millions of years. These stellar encounters could eventually redirect the comet into entirely different regions of the Milky Way. The comet may eventually approach another star system, where it could be captured into a new orbit, becoming a permanent member, or continue its endless wandering journey. If captured, 3I Atlas could become a permanent member of an alien planetary system, carrying chemical signatures from our solar system to worlds beyond human imagination. Alternatively, the comet could drift through interstellar space for billions of years, never encountering another star, slowly degrading under the relentless cosmic radiation until only a dark, lifeless remnant remains. The organic compounds and water ice that define its current composition will gradually transform into simpler chemical species. However, the scientific data collected during 3I Atlas's brief visit will continue to provide valuable insights long after the comet finally disappears from view. Detailed analysis of spectroscopic measurements, brightness changes, and compositional data will occupy researchers for years, revealing new understanding of planet formation processes throughout the galaxy. Future interstellar visitors will inevitably be compared to the properties of 3I Atlas, creating comprehensive databases that shed light on the astonishing diversity of planetary systems and the mechanisms that eject objects into their galactic wanderings. The European Space Agency's Comet Interceptor mission, slated for launch in 2029, represents humanity's best hope for achieving unprecedented close contact with an interstellar visitor, potentially including 3I Atlas if trajectory calculations prove favorable. Colin Snodgrass, an astronomer at the University of Edinburgh actively working on the ESA mission, explains that there's a small chance that Comet Interceptor could visit an interstellar object if one is found on the right trajectory, and the new Vera C. Rubin Observatory should give us an increased detection rate of these objects. The Comet Interceptor spacecraft will patiently wait in space at the L2 Lagrange point, strategically positioned to intercept any suitable target that comes within a reasonable distance. This unique Sentinel strategy allows for rapid deployment to objects discovered after launch, including potential interstellar guests that cannot be predicted in advance. This mission represents a unique endeavor consisting of 3 separate spacecraft, each approaching the designated target from different angles. This configuration will provide comprehensive 3-dimensional observations that are impossible to achieve from a single vantage point. Such a multi-spacecraft formation could radically change our understanding of the internal structure and chemical composition of interstellar objects. Aboard the Interceptor spacecraft are advanced instruments, including high-resolution cameras, mass spectrometers, and dust analyzers. These devices are capable of precisely determining the chemical composition and physical properties of the materials being studied. The measurements obtained will provide unprecedented detail about substances that have arrived from another star system. A successful encounter with an interstellar object would be one of the most significant achievements in the history of space exploration, comparable in importance to the first human landing on the Moon or the Mars rover missions. The scientific returns from direct analysis of extraterrestrial materials could answer fundamental questions regarding planet formation and the potential for life throughout our galaxy. The mission's tight timeline creates a pressing need to maximize opportunities for observing 3I Atlas and future interstellar discoveries. Each new cosmic visitor provides additional targets for potential spacecraft encounters, while simultaneously deepening our understanding of interstellar object populations and their trajectories. Sample return missions remain the ultimate goal for interstellar object science. Bringing fragments of alien worlds to Earth for subsequent laboratory analysis would provide information unobtainable through remote observations, potentially revealing complex organic compounds or even biosignatures. Advanced propulsion technologies currently under development could enable rapid response and quick missions to newly discovered interstellar objects. Ion thrusters, solar sails, and nuclear propulsion systems are capable of allowing spacecraft to achieve the high speeds necessary to intercept the trajectories of such objects. International cooperation will play a crucial role in the successful implementation of missions to study interstellar objects. The coordinated response of the global astronomical community to the appearance of 3I Atlas demonstrates the collaborative foundation needed for future spacecraft encounters with these cosmic wanderers. Object 3I Atlas represents much more than just an astronomical curiosity. It serves as a cosmic messenger, carrying profound implications for humanity's future in space and for our understanding of the potential for life throughout the galaxy. This interstellar visitor directly connects us to the wider universe, reminding us that our solar system exists in a dynamic galactic environment where material and information freely move between star systems. The chemical signatures preserved in the ancient nucleus of 3I Atlas provide direct samples of conditions that existed in another planetary system billions of years ago. Every spectroscopic measurement and every compositional analysis adds important data to our growing understanding of planet formation processes throughout the galaxy. The accumulation of observations of 3I Atlas and future interstellar visitors will eventually enable comprehensive statistical analysis of conditions in numerous stellar environments. The diversity of interstellar objects likely reflects the vast diversity of planetary systems across the Milky Way. Some visitors may arrive from systems dominated by gas giants, others from regions rich in rocky worlds, and still others from environments unlike anything in our solar system. Each messenger carries unique information about its place of origin. The discovery of complex organic molecules in interstellar objects would be one of the most profound discoveries in human history, potentially providing evidence that the chemical precursors of life are widespread in cosmic environments. Even the presence of simple organic compounds would demonstrate that the building blocks of life are common throughout the galaxy. Advanced missions to intercept and study interstellar objects could return physical samples to Earth for detailed laboratory analysis, providing unprecedented insights into extraterrestrial materials and their chemistry. Future spacecraft could be designed to follow interstellar guests back into deep space, thereby extending our exploration capabilities beyond the solar system. Educational initiatives inspired by the 3I Atlas phenomenon are actively contributing to the formation of new generations of talented scientists and engineers. It is they who will develop revolutionary approaches to studying cosmic messengers. Student involvement in genuine research projects provides them with invaluable practical experience that sparks genuine interest and encourages further deep immersion in space science and exploration. International cooperation in the study of interstellar objects creates a solid foundation for the unimpeded exchange of data and effective coordination of observations, which will undoubtedly bring immense benefits to future scientific discoveries. These global partnership networks serve as a guarantee that humanity's response to the arrival of cosmic guests will be as scientifically productive as possible, while embracing the diversity of global perspectives and approaches. The successful observation and analysis of 3I Atlas eloquently demonstrate that our technological capabilities have reached the critical threshold necessary for systematic research of interstellar objects. Modern survey systems, high-precision instruments, and carefully coordinated global observations now provide scientists with all the necessary tools to derive maximum benefit from such rare and unique opportunities. As 3I Atlas completes its rapid passage through our solar system and once again ventures into the boundless expanses of cosmic depth, it will leave behind a transformed scientific community. This community will be enriched with new knowledge, expanded capabilities, and increased expectations for future discoveries. Thus, the era of interstellar archaeology has effectively begun, opening unprecedented horizons for researchers to explore the hidden history of the galaxy through direct analysis of materials arriving from distant worlds. The story of 3I Atlas will forever be etched in the annals as a turning point when humanity truly began to explore the galaxy without leaving the confines of our solar system. This cosmic projectile, hurtling through space at 68 kilometers per second on the most extreme trajectory ever recorded, has fundamentally changed our understanding of what might lurk in the profound darkness between the stars. From its almost unnoticed discovery, skillfully hidden against the backdrop of billions of stars in the galactic center, to the astonishing fact that amateur astronomers tracked it for weeks before professional scientists recognized and acknowledged its alien nature, 3I Atlas revealed critical vulnerabilities in our space surveillance systems. At the same time, it powerfully demonstrated the immense strength of citizen science. The mathematical calculations concerning 3I Atlas are absolutely irrefutable. Its orbital eccentricity of 6.2, speeds that significantly surpass those of all previous interstellar guests, and size estimates that potentially make it the largest cosmic wanderer ever detected. These numbers encode a story of cosmic violence and astonishing survival that spans millions of years and extends across countless light-years of cosmic space. But perhaps most importantly, 3I Atlas has conclusively proven that our galaxy is teeming with interstellar objects carrying chemical fingerprints from alien worlds. John Tonry of the University of Hawaii's acknowledgement that a significant number of such objects pass through our inner solar system each year means that we are literally surrounded by cosmic messengers just waiting to reveal their deepest secrets. The race against time is an undeniable reality. Martian orbiters are preparing to take unprecedented images in October. The James Webb Space Telescope is poised to reveal infrared secrets that remain invisible to the human eye. Ground-based observatories worldwide are coordinating the most intensive and comprehensive study of an interstellar object in recorded history. And then, after its brief moment in our cosmic spotlight, 3I Atlas will disappear forever into the cold void, carrying its remaining mysteries back into the galactic darkness, where it will drift for millions of years before potentially encountering another star system. The future promises even more remarkable discoveries. The Vera C. Rubin Observatory will transform rare visits by interstellar guests into routine scientific practice. Interceptor missions may provide humanity's first-ever close encounter with materials from another star system. Each new cosmic wanderer adds crucial pieces to the greatest puzzle in astronomy, understanding how common Earth-like worlds are throughout the galaxy. 3I Atlas has opened our eyes to the reality that we live in a universe where alien worlds regularly visit our cosmic doorstep. The pursuit of this particular guest may be coming to an end, but the grander journey of cosmic archaeology has only just begun. Thank you for watching, friends. See you in the next video.